Hello, I'm back. We are starting chapter 2, and in chapter 2 of our textbook, we're going to start looking at strain, which is the deformation that occurs when we have stress, okay? So, and then when we get to chapter 3, we're going to look at the stress-strain relationships of different materials. But right now, we've just got to kind of wrap our heads around what does strain mean? How do I calculate it? And, again, I'm going to put up the same slide that we keep having, okay? Because it's just super, super important that we remember that normal stress, normal force just means perpendicular to the cross section. It's like if I pull a rubber band or compress something, okay? So we're going to have a change in length. Our strain is a change in length. Either we get longer or we get shorter. And then remember that shear is that parallel force, parallel stress, and it's going to cause distortion. So this first video, which is going to be pretty short, is all about the normal stress, okay? So when we are looking at normal stress, remember, it is a pull, it is a push. If I over tighten a bolt, it can come apart under a tensile failure, okay? If we look at like concrete, if we look at tension or compression, okay, it's because of that change in length. Shear is parallel to a plane. If I'm shearing a bolt, okay, it's got two plates that we're holding together. I'm pulling one plate to the right, one plate to the left. What is happening? Okay, do you see it's like we're cutting bread? There's actually a distortion of that cross section. So instead of pulling it, and that cross section is going to get smaller as we get longer, or cross section is going to get wider as we get shorter, we are actually distorting the shape of the cross section. I kind of think like side to side. Like think about Jello. If you had a block of Jello, okay, if you had a block of Jello and you kind of pushed it from the top, it's going to go back and forth, right? That's going to be our shear strain. It's a deformation that's an angle change. So deformation, we're going to have both normal, and it's going to be a change in length, and then we're going to have shear, and it's going to be kind of a skewing of where that cross section is, okay? So one place, I mean, do you think these things happen independently, or do you think that a system could undergo both? I'm going to guess most of you have ridden a bicycle before, and when you clamp the brakes, okay, the little rubber pieces close in on your wheel. Okay, as they close in on the wheel, your compression, so you're getting that nice normal force, normal stress, okay? You're also, that wheel is wanting to go forward while we're compressing, so you're getting a shear because there's going to be a distortion of that rubber pad in the direction that the wheels are trying to go to stop it. You can see over here in the bottom right-hand corner, this is a rubber bearing, and you might see these as you're driving to Oklahoma City or something similar to this. It could be like a rollers, but if we have a girder and we're in the state of Oklahoma or in Dubai, which has even bigger temperature changes, with heat, we expand. With cold, we contract. We don't want buckling of our girders on our bridges, so we actually have these rubber bearings, or we could have wheels, but it allows, if you look at that rubber bearing, it is holding the weight of the girder. Okay, so we've got that normal force pushing down. It's in compression. It's going to want to get shorter. If we have expansion or contraction, there's that shearing, so you can see that angle change to the right or to the left as that girder expands or contracts or expands. So we can actually have both occurring at the same time. The other way to think about this is if you're a bike rider and you clamp on that brake, what happens to the brake pad? Compression and shearing, okay? So just two different behaviors. That's all we have. We have normal and shear. So normal strain. What is normal strain? It is a change in shape and size. Okay. If I have a rubber band, it is highly visible. I can stretch it and it is going to, we can see that elongation. If I made a silly putty column, okay, or a Play-Doh column even. How many of you guys have ever taken new Play-Doh out of a container and it's still that perfect cylinder and you dump it on the table and you push down on it, okay? That is compression, okay? we might not be able to see changes. So, I mean, hopefully if we're designing a structure, we don't want to see large deformations, right? We don't want to see that. But you could see like a beam and bending, okay? If you've ever worked on house construction, um, you know, you can see this stuff, but usually we don't. Where else can we get changes? So it's not just from loading, but it's temperature, just like we said. Why is there expansion joints? Why do we have expansion joints in our highways, in our roads, in our sidewalks even, okay? Because when things get hot, they expand, and we need to allow for that, okay? So it's not always necessarily uniform. We are going to be looking at pretty standard uniform elongation. If I have a rubber band, rubber bands are easy, and I apply a tensile load to it, it is going to stretch. As it stretches, the cross-sectional area gets smaller, and we're going to learn how all of that is related. Here's an expansion joint. As the pavement expands, we have room that it can lock together so that we don't have buckling. Okay, have you guys ever thought about why our telephone wires or electric wires, I guess they're probably not telephone wires anymore, they have some sag in them, okay? Because again, when things get cold, they contract. When things get hot, they expand. And so if we hang up a wire, okay, if we hang up a wire when it's 100 degrees and we hang it straight, perfectly straight, what happens when it gets cold and it's wanting to contract? We're going to have lots of issues with our system, okay? What else would be if you are a chemical engineer or mechanical and you work in a processing plant? Many times the piping that's taking air or fluids from one part to another, there are temperature changes in that as well. Even ductwork in our house, right? It's hot air coming out where the blower is. By the time it maybe gets back to a bedroom, the air has changed, but it's still temperature changes. So it's everywhere. Okay, so if we have normal stress, that is sigma, it's N over A, it's that internal normal force over that cross-sectional area, right? The resisting internal cross-sectional area. We assume that stress is average. Each little point is undergoing the same amount of stress. Strain, this is normal strain, okay? Normal strain. It is associated with normal stress. It can be measured experimentally. Normal strain changes the bar length. We could have elongation, positive, that's tension. If I have a positive stress, because I have an internal normal that's positive, I'm going to have elongation. If my internal is negative, if it's negative internal normal, it's going to be a negative stress, contraction, getting shorter, which is why it's important to keep up with, we always assume positive to figure out if it's negative, okay? Our strain is dimensionless, okay? It's a dimensionless value because it is change in length over a unit length, okay? Change in length over length. I want to know if I heat up this wire, I just need to know the inch per inch amount it's going to change in length so that if I have 100 inches or 1,000 inches, I know what to expect. So it's a unitless because it's an inch per inch. It's a meter per meter, a millimeter per millimeter. What does that mean? If it's going to stretch an inch for every inch, that's going to be pretty stretchy, right? Okay. So normally it's, it could be maybe 0.1 inches for every inch. That would still be very stretchy, okay? So it's change in length over length. It's the original length goes on the bottom. It's always the original length on the bottom. On the top, length final minus length initial. So what happens if we contract? That length final is shorter than the original. We have a negative strain. So if I see negative strain, getting shorter. If I see a positive strain, getting longer, okay? And we can talk about microstrains. Like, what is a microstrain? I've never heard of that. It's just basically e to the negative 6. Instead of having a 0.000475, we could call it 475 microstrain inch per inch. So we're not writing like very long decimal numbers, okay? It's just times 10 to the negative 6. You can put it with inches, you can put it with meters, it doesn't matter. It's just I don't want to have little teeny tiny decimals, so I can write it as kind of a bigger number, 135 microstrain. I know it's really 135 times 10 to the negative 6. Those of you in strengths lab, you probably have already been doing this. Okay, so again, normal force, normal stress, tension, elongation. Normal force, normal stress, compression, shortening. And it's just, we're looking at that perpendicular force on an area and how it affects. That's the strain, change in length over length. There you have it. That's our new formula.